Okay. Could you see, please, my screen?
Yes, I can.
Okay. I will change the camera to what I'm doing. Okay. So I have connected the Arduino with the 4-digit display to the computer. It's a similar hardware that we have used on another exercises. This Arduino Uno, it's connected to the 4-digit display. We have made on the last exercise the program, the display driver, which is displaying the 4 digits, and this is the program. The program is very similar to that on the last exercise. The change is in the mapping of the output pins, because these pins fit on this Arduino. I have used 4 PNP transistors, which are switching the digit anodes, and the cathodes of each segment are connected through a resistor to the microcontroller. Can you hear me, please?
Yes.
Yes, okay, because I have changed to my headphones. Okay, thank you. Okay, this is the program which is defining the mapping of the I/O ports. These are the this is the program for clock. Okay, what we will do first, we will turn on the analog to digital converter to see an analog value connected to the microcontroller, and then we will proceed, I hope, with some digital processing of this value. Okay, what we have to do first is the switching on of the analog to digital converter. So this is the datasheet of the Arduino microcontroller. It's not 80 mega 16, it's 80 mega 3 to 8 with P. P means picopower, which is designed for battery operation. Okay, how we will turn on the analog to digital converter. Analog to digital converter. Register description. And we have several options to operate this analog to digital converter. First, we choose the reference voltage. So we have to set up this register addmux, and we will use the AVCC as reference voltage. It means that we are using 5 volt because this microcomputer is supplied with 5 volts. AVCC, it's reference selection 0 bit, it's set up to 1. Okay, what next? Left adjustment result. We will not use the manipulation of the left adjustment because we want to assemble this value to a 16-bit value, 16-bit variable. What about the input that we are selecting? We have to select another input that is used by a display, and I will try. Okay. Okay, the analog inputs are marked on Arduino as AD1 till AD6. I will check if some are used. Yes, they are used, but the A5, it's possible to, it's still empty. So we could connect the value from the resistor, the voltage from the resistor we could connect to the, but it's still connected. It's connected to A0. Okay, perfect. We will make the program and we will see if it's working. So the pin connected, it's A0. Can you see on the camera the Arduino or not?
Yes.
Yes, okay. So we have connected to the A0 and to ADC 0. Okay, A0 is what? Which one? It's probably this one. Yes, it's AD0. Fine. So we don't have to set up the multiplexer. It's switched already to the AD0. What we are setting? Nothing in the ADMUX register. So the ADMUX register is done. Analog to digital converter status control and status register A. Okay, here is nothing else. AD enable. This is turning on the analog to digital converter. Okay, the next bit. Start conversion. We have to start the first conversion to the next bit which we are configuring is the auto trigger, and this will trigger the next conversion in the end of the previous conversion. So we have to set up the next the triggering of the analog to digital converter. Okay. Starts the first conversion. Okay, next one. Auto trigger enable. The auto trigger means by analog to digital converter that the analog to digital converter could be triggered, for example, with an timer event, for example, compare match, overflow, or something, or could be triggered by external interrupt or so. This we will use the free running mode. Free running mode means that in the end of the one conversion, we'll immediately start the next conversion. So the auto trigger is on. Interrupt flag, we are not using the interrupt flag, but we have to use the interrupt to read the value. Okay. It is interrupt enable. Do you understand it, or it's if you have some questions, we could stop and we could explain it more. The interrupt is on, and the last 3 bits, it's a division factor between the microcomputer clock and the ADC clock. The ADC clock, it's slower than the microcontroller. For example, when you have division factor 2, the first conversion, it's usually 20 or 26 ADC clock cycles, not microcomputer, but ADC clock cycles. And the every next conversion has duration of 13 clock cycles. But I mean ADC clock cycles, not microcomputer. Microcomputer runs very fast, 16 megahertz. But when you have, for example, the division factor 16, it runs the ADC clock on 1 megahertz. But we will use the slowest mode. When you have, for example, 128, the division factor, the microcomputer or the Arduino runs at 16 megahertz. It's divided by 128. This is the clock of the ADC converter, but this every conversion is 13 cycles of the ADC converter. It's about 10 kilohertz of sampling rate. The sampling rate is for our purpose, it's very fast. But when you have, for example, 2 audio channels, you have to do it faster, because this is very slow for audio. Okay. So we will set up all these 3 bits to get the slowest clock as possible. Okay, do you understand it or not?
Yes.
Okay, thank you. Okay, the next we have launched the um, auto trigger enable, and what is the trigger source of the analog to digital converter? This is the value written in the two output registers. This will be the analog value. For our purpose, it's left adjustment result 0. It's a better option because we have better assembling these two registers to a single 16-bit register. Okay, the auto trigger source. What is the auto trigger source? Okay, the auto trigger source, it could be selected for in the ADC SRB register, but initially there are 3 zeros, so there is the free running mode. We will use the free running mode, so the first complete conversion triggers the next conversion immediately without any reason. So one conversion will be done and the next will be triggered. So this is the free running. The analog comparator could be used also as a trigger or external interrupt or timer counter event or something. This could be used, for example, when you are measuring, for example, an amplitude of the signal. For example, sine wave from the mains when you have like triac control of a load, then you could measure what is the amplitude, for example, to measure the amount of the electrical energy flowing to the load or something, or triggering the triac in a certain moment or so. Or measuring the shape of the signal, if it's sinus wave or triangle or so. This is the option that you could use on this microcomputer. So you don't have to launch it in some interrupt. You could do it automatically. We will use the free running mode. Okay. The next we have to program, it's the subroutine for the interrupt. So the magic word, interrupt subroutine, and ADC AD okay. Nie. So the name of the vector is ADC vector. Okay. And the subroutine, it's we have to make a variable. Best option is to use the magic word volatile, because when you are not using the volatile before the variable, the program will, the compiler will look, and if there is no, if you haven't used it in main, the compiler will not translate it. This is the danger of using interrupts. So for example, we will name it voltage. Okay. So this is all. And what next? We will try to display it on the display. Okay. So these are the digits to display. Okay. Do you understand this dividing this modulo 10, which is displaying the we are splitting this voltage, which is from 0 to 1023, to the 4 digits. Do you understand it, or it's too difficult?
No, it's okay.
It's okay. Okay. These are the thousands, because the voltage could be above 1000. 5 volt means 1023. So it's 5 volt. So we have, I think, 20 millivolt. No. Uh, 5 millivolt, near 5 millivolt per one analog least significant bit. So these are the thousands. When it's above 1000, it's 1. When it's below 1000, it's 0. This voltage modulo 1000 means hundreds. For example, when the voltage is 524, modulo 1000 gives you 524 divided by 100, it's 5. So these are the hundreds. This is voltage modulo 100 means 524 means 24 divided by 10, it's 2. Voltage modulo 10, 524 modulo 10, it's 4. Okay, I try to program it. Okay, it's not working. Okay, now it's working. Okay, the disadvantage of putting the value directly to the display is that the last bit it's changing. Sometimes it's measured as 149 or 150. So now you cannot see if this you cannot put the direct analog value to the display because it will be it will contain some noise and it will be very it will be not clear for the people to see it. So in your opinion, what is the solution to make the displayed value stable? What is your proposal to make the value stable?
Can you repeat, please?
For example, when the value is changing between 149 and 150, it's not clear to see which number is on the display.
Yes.
Yes. And what do you think what we could do with this displayed value to have it clear for the people to see it clear? Not changing every like 100 times in a second because you can't read it.
We should slow down. If you want.
Okay, this is the one option to slow down. Okay, we can try it. So we could use this timer, for example. We will have the next variable. Okay. We will change the voltage to the displayed number. Okay. And we will use the 1 second interrupt to update the value on the display. Here is the 1 second interrupt. And we will use, for example, displayed number is voltage. This means okay. Okay. We should declare it before this function with the using. Okay. Okay. It's better? What do you think?
I don't really see on the camera. At least I can see that it's not changing really fast, so we can read.
Yes, but it's still containing the noise.
Mm.
It's from 148, 46 Or,
Yes.
I don't know if can you see it better or not?
It's 152 now.
This is better, or which was better? This one?
I mean, I have two cameras. I have your screen with the entire webcam, but it's really small, and I have the return on the right. It's smaller, but I can see it's like a bit bigger, maybe a bit on the left. No, so the right, it's a reverse, sorry. Okay, so it's 147, 49. Yeah, okay.
Okay. So this is still containing the noise. What has changed is only that we are throwing away near 10,000 values, and we are picking only one in a second, which we are displaying. So we are losing some information what is between these two samples. This is the first point, and the second point, it's still containing the noise. Okay, how we could remove the noise?
I don't know.
Okay, we could use digital filtering. Digital filter is similar to analog filter. Have you learned something about analog filtering, like coils, capacitors, and connecting it to low pass, high pass? Have you had some subject?
Yes, we had it, but it was 1 year ago already. So
Okay, so the principle of filtering is in the digital domain is a little bit another. You are, for example, taking samples with some sampling rate from the signal, and then you are applying on this vector of samples or this row or series of samples, you are applying some digital filtering. A digital filter works that you are multiplying and adding the samples with some numbers. And depending on the weight numbers, you are doing low pass or high pass filter or band pass filter. This is how, for example, works that when you are setting your MP3 player or computer or television to get the more bass in the audio or less, or more treble or less treble or something like that. This is how the digital filtering works. And what about the numbers? How we will use the digital filter? The digital filters are divided into two groups. Okay, we'll make some short introduction. Okay, very briefly, what is the difference between infinite impulse response and finite impulse response? These are the two ways that you could program a digital filter. Okay, the finite impulse response uses, for example, the last 100 samples and processes only the last 100 samples. This is the finite impulse response. The infinite impulse response works that you are putting the last sample on a big amount of added numbers and dividing it by the some number. But this big amount of last added values contains some relics from 1 week ago. So the practical difference between infinite impulse response and finite impulse response filters. Finite impulse response, which is processing only last 100 or last 1,000 samples, is that it's stable. It's not fluctuating. But it's more. It has a higher demand of the microcomputer memory, the finite impulse response. The infinite impulse response uses only two variables in the memory. And it could be programmed, for example, for 10,000 samples or million samples. It doesn't matter. It has only two numbers. So we could see how it's implemented a low-pass filter in the microcomputer. Okay, we will use the array as a series of samples. And we will make a cycle, or we could write it below each other. Okay. Okay. Do you understand what is here, what I'm here doing?
You just delay of one, like you're putting the value of the next one to the previous one.
Yes. Yes. So I have last 10 samples of the voltage. Mm, okay. It could work. Okay. Reading the ADC to voltage. Okay. The wrong brackets. Okay. 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 Can you see the camera?
Yes.
Okay. What do you think? What has changed?
It's moving fast between 150 and 51.
Yes, but the noise,
Yes.
the fluctuation is not from 140-60 till 150 and I don't know, but it's between 150 and 151.
This is what I said.
Yes. So when we are making the average of this finite impulse response, okay, I will note it to the code. This is the real implementation of finite impulse response filter. Pass. Okay. It is clear.
You're divided by 10 due to the series of samples for the voltage.
Sorry.
You divide it by 10. It's due to the for the voltage because we are from 1 to 10.
Yes,
Yeah.
I'm dividing it by 10. If I would divide it by another number, it will give you not the real value. For example, when you choose another value, can you see it?
Yes.
It's 300. It's not okay.
Yeah.
So I will give there 10. Okay. Now we could try to implement the infinite impulse response filter. The infinite impulse response allows you that okay, this I could make it before the definition, before the but we have to use another type of variable, and it will be float. But we have to convert the I will try to compile it, but it will be probably not successful. Definitely, I have to use the float type of variable in the infinite impulse response. But there are some changes in the microcontroller how to change the float to integer. Okay. No. Jeszcze 20 minut. Do 10:40. Okay, we will try it. Okay, we will try it. Okay, it's not working. Okay, it's not working now. So we will make it on the next exercise that we will implement the infinite impulse response, because I have some problems with changing from floating point to integer, because it has some uh, uh, bugs uh, in the 8-bit microcontroller. Okay, so probably the infinite impulse response filter we will program next time. Okay.
Okay. And I have two questions.
Okay.
The first is, sorry. The first is, do we still have classes online, or we will go to university to have class with you?
No, the classes will be only online.
Okay, only online. And due to lockdown, so you say we can't move to another city, but can we move to another country?
Uh,
Like out of,
uh, I don't understand which country.
like for example, if we have to leave Slovakia to go back to France, or if we have to go to Hungary or Austria to take a plane, something like this.
Uh, I think you can go there.
Mhm.
The If you tell the police, for example, that you are going back home, it's okay.
Okay,
But
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 not for tourism.
when you are going only for a trip, for example, to Bratislava, it's not a reason to go there.
Okay, yes.
Okay.
Okay,
Okay. So we will try to implement the infinite impulse response filter next lesson,
okay,
and we will see what will happen. Okay.
okay. And for
Oh,
the day, we still have this on Thursday, or we go back on Tuesday morning?
uh, I will ask other students
Mhm.
which have attended this course, English, if they have some lessons on the first day morning, and if they don't have the schedule, we could have it on Thursday. But if they have some scheduled lessons, we will have it for example, on Tuesday at 9 o'clock or so.
Okay.
I will let you know by Teams.
Okay.
Okay.
So thank you very much and see you next week.
See you next week. Have a nice day.
Thank you.
Bye.
Bye.